Hi, this is Mark Weitzman. Welcome back to Quantum Field Theory, a student's perspective. Today I'd like to have a recitation on a problem in Mark Srednicki's Quantum Field Theory textbook. This is the problem. As I mentioned many times, the draft of the book is freely available online and you can get the PDF file, and this will be included in there. It's a fairly straightforward problem. We've already done many of these calculations, but I'll just do them again, painfully slowly, just so that these calculations become second nature. So this is lesson 3. Excuse me. Recitation. Problem 3.4 in Srednicki. So, the first part of 3.4 says that we've established, and I think we've done this many times, we might not have used the exact notation T for the translation operator, but and T, the translation operator, is defined as the exponential generated by the momentum operator. A is a parameter. Okay, so the first thing it says to work out is assuming our parameter is infinitesimal, so that implies that T of A is approximately 1 minus I P mu A mu, and T of A inverse, sorry about that, it is true what I wrote, but T of A inverse is approximately 1 plus I P mu A mu. And this is because P is a Hermitian operator and A is a real parameter. It's a translation in space. So substituting this here, we would get 1 plus I P mu A mu phi of x 1 minus I. Now I'm being like super careful here by using different indices in different terms because they might interact. It turns out they don't, but and then we can expand this using the usual Taylor expansion. So, keeping only terms to first order, we're going to get phi of x plus I P mu A mu phi of x minus phi of x. Now I'm going to, well, I'll keep the index for now, but you can see that we can use the same index. It's a dummy index. So the phi's cancel from both sides of the equation, and we're left with I. Now we can change this to mu so that we have the same term here. We're going to get I A mu, the commutator of P mu, comma phi of x is equal to minus the partial of mu. Keep doing that. I don't know why. Oh, all right. Oops. What I want to do is put the indices in the same places. So. Okay, so because we have a mu on both sides, and this holds for any parameter, we can sort of cancel this. And so we're left with p mu phi of x is equal to I partial of mu upper phi of x. Okay. That's what we wanted to establish. So we're good. Now in part B, we want to show that the time component of this equation that we just established is the equivalent to the Heisenberg equation of motion. So the time component of this equation is p0 phi of x. Now, remember, we're using the East Coast convention. Uses metric. So when we raise and lower time indices, we get a minus sign. So over here, we're going to get minus I, the partial with respect to t, of phi of x. And so we can bring the I onto the other side. P0 is nothing other than the Hamiltonian. Phi of x is equal to phi dot x. And that is, in fact, the Heisenberg equation of motion. So we're good there. Okay. Part C says for a free field, use the Heisenberg equations to derive the Klein-Gordon equation. So we have, this is one of the Heisenberg equations of motion. Phi dot x equal to I, commutator of h comma phi of x is equal to I, commutator. Now you can look back in the book as to what the Hamiltonian is for the Klein-Gordon field. It's pretty easy to remember. Pi of y squared plus 1/2 del phi of y squared plus 1/2 m squared phi of y squared comma phi of x. Okay. So this is equal to, the only thing that's not going to commute with phi, this will commute with phi, and this term commutes with phi, and this term commutes with phi, because all phis commute with each other, and taking spatial derivatives and everything doesn't matter. It's only the pi. So we're going to get I over 2. And we can also take the integral out of this expression, out of the commutator. Pi over 2, the integral of d3y times the commutator, pi of y, comma, phi of x. Okay. And using the usual Leibniz rule for commutators, which is always very helpful, we get pi of y, commutator, pi of y, comma, phi of x, plus the commutator of pi of y, comma, phi of x. Okay. This is equal to I over 2, the integral d3y. I left out the pi y here. Both of these terms are going to be equal. This is a delta function with a minus I sign. So I'm going to get minus 2I pi of y del 3 x minus y. And our final result is phi dot x equal pi of x, which we know and we established a long time ago when we went from the Lagrangian to the Hamiltonian. Okay, that we knew. The more interesting equation is pi dot x is equal to I, the commutator of the Hamiltonian, with pi of x. This is the other Heisenberg equation of motion. I should just copy it from there, but I think it'll be easier for me to write it again. Okay, 1/2 pi y squared, 1/2 del phi y squared, 1/2 m squared 5y squared pi of x. Now we have to treat these terms. This term we can ignore, but we have to do these two terms. Okay. Also, since we have pi of x is phi dot x is phi double dot x, we might as well do that substitution. I, taking the integral outside of the commutator again, so continuing, now it always helps to use the Leibniz thing. This is, after all, I'm not putting vectors on top of the del's, but they're there. Okay. And this is equal to, using our Leibniz rule again, we can, it's really like three terms here, but we're using vector notation. That's why I put that's a dot product. Okay, continuing to plug and chug and grind along. Now what I'm going to do to evaluate this commutator, I just take the del out of here. The operations commute when you, so you might ask your local mathematician for some rigorous justification of this, but it does work. So I'm going to get a del and obviously the argument of del is like it's y. That's where it originally occurred. I mean, I'm not writing del y's like I should. And then this term, we know how to evaluate these commutators, and they're the same. So we get 2m squared I 5y del 3 x minus y. Now, what we do with these two terms is we integrate by parts. So that we're going to get the gradient off of the delta function. So this then becomes minus I over 2, because I'm integrating everything by parts in here. The integral of d3y. Once you integrate by parts, this becomes del squared phi of y, and both these terms become the same del squared phi of y, and the commutator is the same. So we just get 2 del squared phi of y. Then the commutator itself evaluates to a delta function. Then I have plus 2m squared I phi of y del 3x minus y. Okay, so finally we're going to get phi double dot x is equal to, the i's make that positive, the 2's cancel, and then the integration over the delta function just changes x to y. So we get del squared phi of x. Over here, well, okay, I put a minus sign here, so this should be a minus sign. So over here, I'm going to get minus I times minus I, so it's minus, so I get minus m squared phi of x. And this is the same thing as phi double dot x minus del squared phi of x plus m squared phi of x equals 0. That's good. That's our Klein-Gordon equation. Okay, part D. We define a momentum operator. This is a capital P minus the integral of d3x pi of x. Here I will put vectors on top of the del's because that's where it comes from. So we want to show that the commutator of pi, that's the spatial index I'm just using, is equal to I times the partial of phi of x with respect to I. Here I is don't ever confuse a spatial index with the imaginary I. That's why physicists are smarter than engineers. We can live with the imaginary I. We don't have to invent a new symbol with it and put a J in there. Okay. That's just a joke. I hope no engineers are offended. There's a famous quote by Dyson. I recommend you look it up, where he says that the difference between a physicist and an engineer is that for a physicist, you want them to solve problems in like the most creative ways possible. Whereas for an engineer, you want to solve the problem using the least creative ways. You want to you might have a creative solution, but you want it to, and you have to look up the exact quote because I'm really like mangling this, but the engineer sort of uses what's already known and solves the problem in the most economical, least likely to fail fashion. So they sort of work in opposite ways, but it still requires a lot of creativity on both sides. Okay, back to theoretical physics. So let's just evaluate this. Pi phi of x to minus the integral of d3y times the commutator of, just substituting in this definition over here, times the commutator of pi of y, the partial of I, phi of y, comma, phi of x. Okay, this is equal to minus the integral of d3y, do the usual Leibniz rule, okay. Okay, so this vanishes, as I said. Fields and derivatives, spatial derivatives, they always commute with each other. It's only time derivatives that you get into canonical momentum. So that vanishes. So I get minus the integral of d3y. Then I'm going to get minus I del 3x minus y, partial of I, phi of y, which is equal to I, partial of I, phi of x. That's what we wanted to show. Okay, last part of the problem and the longer part. Again, P is defined. We want to express P in terms of annihilation and creation operators. Okay, so just as an aside, the fields, as Srednicki establishes in the book, is equal to the integral of d tilde k. This is the covariant integration measure. Just remind you, but we're only going to use this at the very end. a of k e to the I k dot x plus a dagger k e to the minus I k dot x. These are 4 vectors, but they're constrained 4 vectors. In other words, the time part is omega k. Sorry. So we're always using this notation. So that's phi. So you can see when you take a gradient of phi, you're just going to get an I times the vector of k from this term coming down, and a minus I times the vector of k from this term coming down. And pi of x is equal to phi dot x. So when you take a, so this is going to be like the integral dk tilde. I'm going to write this in the schematic form, ae to the I kx. You're going to get a minus ik, because remember the metric Srednicki is using the time term, and this will be minus. So I get a minus I omega k, and then plus a dagger dot 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 times an I omega k. Okay. So now we just got to substitute this in there and this in there. You know, we use different variables each time. So p is equal to the integral of minus the integral d3x, the integral of dk tilde, the integral of dk prime tilde, and now I'm going to have 2 terms here. This is not a commutator, this is just a bracket. ak e to the I k dot x minus I omega k plus a dagger k e to the minus I k dot x I omega k. That bracket is multiplied by ak prime e to the I k prime dot x times I k prime plus a dagger k prime e to the minus I k prime dot x minus I vector k prime. Okay. Now let's do I'm going to do the x integral in our heads. We're going to have 4 terms, and there's always going to be a delta function here. It's either delta k plus k prime or delta k minus k prime. And we have this minus sign, and this minus sign is going to change on these. So you can check that I'm going to do this right. The integral of dk tilde. And then when we integrate over the exponentials, we get a 3-dimensional delta functions. So we no longer have an integral over x. I'm doing that in my head here, as should you. We get a 2 pi cubed, because the integral of an exponential is 2 pi cubed. Now I have 4 terms. I'm just going to write them out. ak k prime minus omega k prime. Just to show this, if we take this over here times this, I times minus I is plus, I get an omega k and a k prime. This should be a vector here. And we get the exponential for the time factor that we didn't evaluate, e to the minus I omega k plus omega k prime times t. You can see it's the same sign in the exponentials. And then we have the del 3 k plus k prime. Okay. I like to do the a's first, and then I like to do the a daggers first. There's a good chance in copying this stuff from my notes that I'll make a mistake, but the end result is going to be right. And these are the over here is the important terms, the ones that will survive, as we'll see. And our final term. So this is very similar to the calculation that's done in the book to get the Hamiltonian, except now we're doing it for the momentum operator. Okay. Let's rewrite that whole thing. Okay, so now we just evaluate all these delta functions. First of all, using this metric here on the dk prime tilde, the 2 pi cube here will cancel this thing over here. And then we're going to have a 2 omega k. All of these delta functions evaluate so that omega k is going to be the same. So that's going to cancel all the omega k's in here. So all these omega k's go. And we're left with the integral of d tilde omega k. We still have the 1/2 from there. 1/2. Now we're going to get 4 terms again. I'm going to get k Okay, so let's look at this term over here. When we do the delta function over k prime, it says k prime equal to minus k. So this becomes a plus k. K, ak, a minus k, e to the minus 2I omega k t. And then I have plus k, a dagger k, a dagger minus k, e to the 2I omega kt. And then I'm going to have plus, and now these last two terms are going to be the same. I wrote this wrong. There should be no dagger there. Okay, so we're going to get two terms here. But when we do the integrals, k prime is now k, and these exponentials vanish. So I get a dagger k, ak, and then I have a k, plus k, that term, ak, a dagger k. Okay. Now, my claim is that these two terms vanish, and they both vanish because if you do k goes to minus k, remember that the creation and annihilation operators, they each commute with each other. So if I do k to minus k, for instance, on this term, I end up getting a minus k, a minus k, ak, and it doesn't affect the exponential term. These two can be written in the other orders, so I basically just get negative of what I had before. So if you make on an integration, if x goes to minus x, then it's 0. Same thing here. So those two terms vanish, and we're left with our final result. Well, this is not really our final result, but so this is what we're expecting. It's the same thing as the Hamiltonian, except it has the momentum vector here. In this particular case, we can make use of the commutation relations. And we can write this as now I have 2 ak, I'm sorry, this is the way we usually write it. Now we get the 0 point term. A dagger is a dagger a plus del 3 0. With the convention Srednicki is using is a 2 pi cubed and a 2 omega k here, I think. But it doesn't matter. Unlike the 0 point energy for the Hamiltonian, this is just an integration of a vector. Again, k goes to minus k, and it's 0. So this, we don't have to worry about the 0 point momentum. So finally we get p is equal to the integral of d tilde k, k, a dagger k, ak. So it's a nice result. It basically says that each each oscillator has momentum k. Each particle, and we're going to integrate over all k, and each one has momentum k. So that's it for lesson 3, and I will go back to start on lesson 3.5. I've decided to add a lesson on symmetry, gauge invariance, Yang-Mills non-abelian gauge theories, all from a classical perspective. So I'll see you next time. Thank you very much.